So good morning. We'd like to welcome you to the webinar on HEC RAS. I'm Troy Woodyard, and I'm an EIT in Central Office Highway Design. And our goal here is to kind of take you from a background knowledge. Maybe you've had the HEC RAS class or done a little bit of drainage work, but you don't really know where to begin creating a HEC RAS model. So what we're going to do this morning is begin with when you get a project and you begin with the surveying, and then we're going to go to how to lay out your HEC RAS cross sections, and then finally how to import the cross sections into HEC RAS. So let's jump right in. The first thing you're going to want to do when you've got a project that you want to do a HEC RAS model for is to go ahead and do a site visit. And while you're out at the site, be looking at the topography and try to look at it from a hydraulic perspective. A lot of times as roadway designers, we kind of get in the geometric bubble where all we're doing is looking at the road. But you're going to want to be looking at your drainage areas and your discharge points, low spots, cross drains, nearby structures, and kind of just looking at the project from a hydraulic perspective. And be sure to take a whole bunch of pictures. It seems like I always get back to the office and I need a picture that's, just a little bit to the right of the one that I took. So be sure to take just a whole lot of pictures while you're out there, so that when you're in the office, you can do some more research. Another good idea is to you need to look at your cross sections based on changes in topography. If you remember that from the HEC RAS class, it's kind of interpolating the ground data in between sections. So if you have any abrupt changes in channel size or N value or floodplain width or anything like that, you're going to want to get a cross-section at the beginning and end of that change to try to represent the hydraulic area correctly. Be sure to coordinate with your survey crew when you send them out. Have them get things like finished floor elevations. You're probably going to want to possibly even stake out those cross-section locations if there are cross-sections that you need specifically based on the changes in topography. And either you need to measure the bridge, or maybe they do, so you can compare the shots that they get on the bridge and just make sure that those are indeed accurate. And you need to let them know how far they need to go and then how wide the cross-sections need to be. Another thing that we're really pushing in central office drainage is to get some historic high water information. One of the best ways to do this is to try to knock on some doors and talk to the property owners. Some of the best information that we can get hydraulically is witness high water, and it goes a long way towards validating your HEC RAS model or letting you know, wait a minute, this might be a problem. So after you make your site visit and you get the surveyors sent out, the next step is to gather all of your electronic data. The first thing that I like to do is inspect the DTM. You're going to get something from the surveyor, and he's probably done a pretty good job of going through it and checking everything when he delivers it to you. But I just like to go back and look at it one more time just to make sure that the DTM makes sense with the survey shots and with what you've seen on the site visit. The HEC RAS model that we're going to pull in this morning is cross-sections that are draped over a DTM. So our HEC RAS model is only going to be as good as the triangles that it's created from. The next decision you're going to have to make is how I'm going to get my floodplain data. And if you remember from the HEC RAS class, your cross-sections have to extend far enough laterally to get outside of the high water elevation. If not, HEC RAS will draw a vertical line at the edge of your cross-section, and it'll pretend like you've got a wall at the edge of your cross-section. So you have to get ground data outside of the high water. There are multiple methods that we use in Transportation Cabinet, and we've got them here kind of listed in maybe the order of preference, but this is really a project team decision. You could do a conventional DTM when your surveyor goes out to shoot the rest of the job, and that's probably going to be the best data that you can get. But it's also probably some of the most expensive data you can get. Now LiDAR, we have statewide LiDAR, and we have that available for about half the state right now, and in the next few years we hope to have the whole state covered. And that's very cheap data because we've already paid to collect it. And it's also very good data for hydraulic analysis for the floodplain. It's not good for the channel, and we'll look at that in a couple of minutes, but it's very good data for the floodplain. So if that's available in your project area, you can go ahead and use that. If you don't have the money to conventionally DTM the whole floodplain and you don't have LiDAR coverage, you can get conventional cross sections, and you as a designer can go out and flag where you want the survey crew to take a cross section across, or draw them a map or something, and they can just take a cross section all the way across the floodplain at certain locations, and you can use those for your floodplain cross sections. And lastly, you can merge a conventional DTM with a DEM, and this is the least preferable. The project team really needs to decide if this is appropriate, depending on the type of project and the risk involved. But this can be done, and it is done often. But really, the project team needs to decide how much risk is there and how much cost is involved in the different methods. But the point being, you need to have floodplain data for the length of your hydraulic model. The next step after you've inspected the DTM and gathered your floodplain data is to merge all the surfaces into one surface. So if you've got a DEM or LiDAR tile or something like that, merge that with your conventional DTM, and go ahead and remove your bridge from triangulation so that you've got a defined channel under the bridge. So I'm going to jump over to MicroStation and show you a few things that I look for when I'm inspecting the DTM, and maybe some problems that you might run into. So I've already done a little bit of legwork on this, so I'm not going to go through all the steps today of how to do this, but I'll show you what we've got. So I've got this points file referenced in. So here you can see my survey data, and here's my features. So the first thing I would do when I got this survey, and it looks pretty good to me, is I like to view triangles. Some people like to view contours, but I kind of like the triangles myself. So this is what you would receive from the surveyor. The first thing I want to show you is the bridge. This is the first problem you could run into. If we take and rotate this down, you can see that the edge of pavement features were shot in across the bridge. And so it's triangulating from the bottom of the creek to the top of the bridge. And on this project, if our cross sections fell outside of that fill slope, would be okay. But I like to bring in my internal cross sections this way as well. So that's going to cause us problems down the road. It's probably just a good idea to go ahead on your drainage surface and change those to do not triangulate. So the way I would do that would be to use surface, edit surface, break feature, and break this edge of pavement feature into 3 features, one there, one on the bridge, and one down here. And then just go to feature properties and change this feature to do not triangulate. And I'll show you where I've done that here just in a minute. Another issue I want to call attention to is the long triangle problem. So if you look here, the surveyor shot in these random features here and this break line here. And same thing over here, got another break line. But that was the extent of his survey right here. But InRoads doesn't know that, so it's connecting with triangle from here to there. So for all we know, this could be the hillside or a big cut or something. We have no information on here. So what I like to do is go in here to edit surface, delete triangles, and you can come in here and delete these triangles. So anywhere I see these long triangles that extend outside of my survey shots. I'm just going to go in here and delete them. And what that'll do is that will give you some confidence that the data that you have is actually true when you bring your cross sections in. So I would do that, and I won't bore you with showing you how to do that. But then, if you view the perimeter adjusts to the triangles you've drawn, and then you can import these graphics back into the surface as an exterior boundary, and that's going to keep those points from triangulating outside of that boundary. So those are the two main things you're going to want to look for, but also just look for inconsistencies in the DTM with what you've seen while you were out there. So the next step would be to merge that with, in this case we have LiDAR data, so you can merge those surfaces, and we are going to have, hopefully in the next few days or weeks, a write-up. It's in process, but it's not completed yet, on how to do that. If you have trouble with it, feel free to call us in the developmental branch. We'll be happy to help you with that, or check on the website and see if we've got that workflow up yet. Also, I think that's going to be our webinar in 2 months. Our normal design webinars is on merging surfaces. So be sure to check back with that. But I'll go ahead and show you. This will be my cleaned up surface. And this would be after I removed the long triangles here. And change that bridge to do not triangulate. I'll show you what that would look like. So it looks like a stream. So I think we're good. So I've gone ahead and merged that with LiDAR for the sake of time, and also because it's probably a crapshoot whether or not your computer will crash when you're actually merging surfaces. It's a little scary. So I've gone ahead and done that ahead of time. And I'll go ahead and won't view the whole surface, but I'll show you what that looks like. So there we have our LiDAR data merged with our conventional survey data. And I just want to point out one more thing. I mentioned earlier that LiDAR is not good for channel data, and I'll show you why. LiDAR doesn't penetrate water, and it also only gives you data on the point that the laser hits. So if it doesn't hit a break line, you won't get a point on the break line. So you can see in this area here what a LiDAR channel would look like, and then you can see here what the actual channel looks like. So don't be tempted to use LiDAR for your whole hydraulic model. It's not really accurate. And that reminds me of something else I meant to say a minute ago, is be sure to talk with your surveyors about what shots you need on the stream. Surveyors, a lot of times haven't been trained in hydraulic modeling, don't know what it is you're doing with the data, possibly. So a lot of surveyors might pick up the bottom of the channel and the top of bank, and then you're going to get a triangular channel that doesn't really describe the geometry of the channel. So be sure you communicate with your surveyor and make sure you get the information that you need. So that's kind of how I inspect the DTM and get the surface into what I need to be able to import the data into HEC RAS. The next step is you have to do some InRoads stuff to be able to do the import process. You need a horizontal alignment from the stream center line, and this has to be stationed downstream to upstream. And what that will do is set the stationing of your HEC RAS model the way that HEC RAS wants it, where the higher station is upstream. The other thing you have to do is bring in top of bank feature, and so that will be a graphical feature that's imported into the surface, and that is also has to be drawn from downstream to upstream. And then the last thing you have to do in InRoads there is to create an overbank feature. And that feature should be placed at the centroid of the overbank flow. And some people are more particular about this than others. The way I kind of do it is I try to get an idea of where the high water is and just draw a line at that contour level, and then kind of split the difference between the top of bank and the limits of where the flood would get. And I just wanted to mention what these actually do so that you don't get too freaked out about making sure that they're extremely precise. The center line gives you the river station that the cross-section's at, and it gives you the downstream reach length for the channel in HEC RAS. The top of bank, the only thing it does is set laterally the location of the bank. So in a specific cross-section, wherever that cross-section crosses the top of bank is where it'll put your bank station. And then your overbank flow is similar to your stream center line in that it gives the downstream reach length to the next cross-section. So you don't want those features to have a bunch of kinks in them and to be crazy lines. They need to follow the direction of flow. So let's flip back over and I'll show you how we do that. Now you can import the surveyed features. Like in this case, I have top of bank feature here and top of bank feature here. I could import those to the surface, or I mean they're already in the surface, so I wouldn't have to import them. But the problem is that they're not continuous, and so if I use this as my top of bank, when I got upstream of the bridge, I wouldn't have a top of bank anymore. So I find it easier to just trace the features with graphical elements and then re-import them. This also lets you take some of the kinks out of the lines that might not be quite the direction of flow. So this bright green line is where I've drawn the top of bank. And so I just traced those features that represent the top of bank. And in this project, water's going this way. So I came from downstream to upstream and just traced that. So that's just a graphical element there. And I did the same thing for overbank. And I'll show you my contours so you can get an idea of what I was doing. Sorry, I'm working on one tiny screen here. I'm not used to that. So as you can see, the floodplain, the water on this project just kind of comes down in between these hills. So this purple line, water gets up around 682, I think, on this project. So I've just got this purple line placed roughly between the top of bank and 680. But you can see how many vertexes I have. I'm not getting crazy here with every 10 feet having a vertex. This is just given the downstream reach length between the sections that we're going to end up drawing. So what I would do would be to import these as non-triangulating features through into this drainage surface that is the merged LiDAR data. So I would just go to File, Import, Surface, and load from single element to the drainage surface. I would drape it on the drainage surface. I could call it left overbank, and then we actually have, I think, some levels on here. I won't bore you. Oh, here it is, existing overbank. And then that would be a break line and exclude from triangulation. And you would do that for each of these features and just name them accordingly. But like I said, I've already done that in the interest of time. The last thing that I mentioned a minute ago was getting a geometry. And so I've already done this too, but it's a stream center line. So I'll just turn off these contours so we can see what we're doing a little easier. And turn the level back on here. So I just use the geometry horizontal curve set tools, add PI, and traced the surveyed center line of the stream from downstream to upstream. And I cut off a few of the meanders, like right here. All that would do would be to lengthen the distance between a cross-section here and a cross-section here. And that's not really accurate when you get to flood stages. So that's all there is to that. And then we're ready to actually lay out our cross-sections. So let me turn off some of this. There we go. And actually, I want to leave on that stream center line. Okay, so the important thing to think about when you're doing your bridge section, this was the most difficult part for HEC RAS for me when I started, and it still is, trying to figure out exactly where these sections go. But the important thing with bridge sections and with any sections is to lay them out looking left to right, looking downstream. And they should turn and go perpendicular to the direction of flow. So we'll look at the shape of those when we put them in there, but they should indicate what area the water has to use in the cross-section. So they can have kinks in them and probably should. The only exception to that is the bridge sections are specified by the Army Corps of Engineers to be parallel to the bridge at the base of the fill, and you'll see that just in a minute. But for laying out bridge sections, you can see here in HEC RAS how you get to this menu. It's under Help and Hydraulic Reference. That's really good for understanding what HEC RAS is actually doing and trying to decode the black box a little bit. But in the Appendix B, it has a nice discussion of where these sections should go and why. And so that's where we're pulling a lot of these recommendations from. So this picture here comes from that appendix. And in the documentation, these sections are labeled 1, 2, 3, and 4. And there are actually 2 internal sections in between 2 and 3 that need to be looked at too. But for today, we're just going to look at sections 1, 2, 3, and 4. So sections 2 and 3 are adjacent to the bridge, and they're at the base of the fill, and they're parallel to the bridge. So those aren't that difficult. We can figure out where those go pretty easy. It's important to note that this Appendix B explicitly states that they're not to be 1 foot from the bridge deck. That's, I guess, an old recommendation or an old habit. I think it had something to do with copying the internal sections and having them look correct, but now the documentation is saying not to do that, but to place them at the base of the fill. So I'll show you how to do that. And I've already drawn these sections, but I'll show you how I would do it. So I dashed them so that when we drew over them, you'd be able to tell what I was doing. So I'm going to get this line style up. Okay, so the first thing I do when I'm doing this would be to get them parallel to the bridge, and the easiest way for me to do that is just to trace that edge of bridge feature. And then I want to move that to the base of the fill. So in this case, there's kind of a ditch line here that I'm considering the base of the fill. So you can see that lines up with where I've got my section. And I would just extend that line out here. And I'm not worrying about left to right or right to left at this point. What I'm going to do is get all these construction lines in and then go back and retrace it. So I'll copy this so that the two sections are parallel to each other to the base of the fill on this side, and I just kind of went with that ditch line on this side too. I thought that was the best indication of where that base of fill is. And since it's hard to hit like right at this point, if you start out here, I like to just start right here. And what you're looking for is, from a broader perspective from the floodplain, which direction is this water going to flow. So this part of the bridge section is prescribed to be parallel to the bridge, but outside of the bridge it should turn and go with the floodplain. So that generally goes up here. And so that's what I would do, and then I'll come back and just retrace that here. And then come up this side of the floodplain here. And that would be my section. I could go back and trim out those construction lines. But the idea here is that water's flowing this way, so it's perpendicular to this line here. So that's how I would lay out those two bridge sections. I do the same thing on this upstream section here. And so that's how I end up with section 2 and 3. I'm going to undo that so I don't get confused when we actually import the data here in a minute. So section 4 is upstream, is the most upstream bridge section. There's a lot of consensus that a 1-to-1 is a good ratio to use upstream, and that's the contraction ratio. If you look in that Appendix B that I mentioned earlier, there's a detailed approach to figuring this out. If you have some special circumstances or something, most of the time at the highway department we're just using 1-to-1 here, but you should look at Appendix B and try to understand the reasoning for that, and if you have any extenuating circumstances you can deviate from that. Just be sure to document that. So what this ratio is based on is the width of the floodplain at the flood stage you're looking at compared to the width of your bridge opening. And so what it's saying is that as you go back in the stream 1 foot this way, you'll go out 1 foot that way. So I'll show you how I figured that. What I did is I measured my bridge opening, and I measured it with the direction of flow. I said flow's roughly going this way, so I'm going to lose a little bit of my bridge opening due to skew. But I measured about 44 feet. And then I went upstream, and this can take several iterations. If you don't guess the right spot, you might have to measure here and then do the math and figure, well, this section should actually be at a different location. Do it again. So it can take a couple iterations, but what I do is go to where I think the contraction length is going to hit and measure the floodplain. So here I said from about 680 to the roadway fill is probably how wide it's going to be. And so you can see these two numbers here. If you do the math, if you do 244 minus 44, you get 200 feet, and then you assume that half of that happens on each side, even though it's not identical, even though it contracts more on this side than this side. The documentation says that you can take the average as far as the location of this section goes, and so then you get 100 feet per side is the average change in width. And so this section is drawn 100 feet from this section based on this stationing. And so I would draw this section the same way I did the others. I might do a station and offset command to draw it from here to here at that station to get it precise, and then go ahead and draw this like I did my other section. So as you can see, it kind of runs with the floodplain just like the floodplains of the sections 2 and 3. So that's for the most upstream section. For the downstream section, it's a little foggier as to how we should handle that. So in that appendix, there's this table, and this is what we're recommending that people use to set that downstream distance. And usually it's going to give you a number between 1 to 1 and 2 to 1. But I think FEMA is interested in us using these values. So the problem with this table is that most of our streams in Kentucky that we're doing analysis on are smaller, steeper than some of the streams that these tables were based on. So it's very likely that the values you get won't be within the range of this table. And if that's the case, don't try to extrapolate the table. Just use the nearest value that you can find in the table. So in this project, the first thing I did was find the N value of the overbank and the N value of the channel to be able to find the NOB over NC ratio. And you can find N values in DR 503 in the drainage manual. I used 0.035 for pasture high grass and for the overbank, and then for the channel I used 0.0425. And that's about a 1-to-1 ratio, so that put us in that first column. The next thing I did was to look at the B over B ratio, and our bridge opening width was about 44 feet, and our floodplain width was about 244 feet, and that gives us a B over B ratio of 0.18, and so that's nearest to the 0.25. It's sort of halfway in between, but it's a little closer to 0.25, so that's what I ended up using. And then lastly, I just cut a profile along the stream center line and measured the average slope of that profile and got about 21 feet per mile, which is about twice as steep as the biggest value in this table. So what I did is I just took this section here, the 10 feet per mile, and I used the smallest value for the expansion ratio because my slope was steeper than this, and as you're moving from flatter to steeper, the ratios are going down, and so I figured I'd use the smallest expansion ratio in that column. So I used 1.5 to 1 for my expansion ratio, and then laid that downstream bridge section out the same way, the section 1. So there are other bridge sections. There's internal bridge sections. These should be edited to reflect the bridge geometry. HEC RAS will go ahead and copy the upstream and downstream sections to the internal sections, but a lot of times that doesn't really reflect what's going on under the bridge. So go ahead and take the time to edit those internal sections and make them reflect what's actually going on. And hopefully next time we can show you a way to do this using InRoads. Also, you can have intermediate bridge sections. You can put sections between section 3 and 4, between section 1 and 2. If you've got a bend that happens just upstream or downstream of the bridge, or you've got something that you want to make sure you get defined well geometrically, you can add sections in between there. Just make sure you also change the expansion and contraction coefficient values in HEC RAS from 0.1 and 0.3 to 0.3 and 0.5 like you would for your other bridge sections. So after you get your bridge sections in, you need to lay out your cross sections, and these have to be left to right looking downstream just like our bridge sections to get the stationing right on them. And you should have cross sections at all changes in topography or changes in N values. Anytime your geometry changes, you should have another cross section. And so usually what I like to do is find all those places where I definitely need cross sections, and then just fill in the gaps with 50 to 100 foot spacing, just to to try to get a good representation of the reach. And so that's how I've done this. And if you'll notice, these all look, like they're going with the floodplain here. So a couple of things I want to point out is I may end up with a problem right here. If you'll notice, this cross-section runs up this drain here. And so I'm actually telling it that it has more air. I possibly could be telling it has more area than it really does. So just be careful when you see stuff like that. Take a look at it. If my water only gets up to 680, it probably won't matter. If my water gets up to 690, then I might be adding another 80 feet to the floodplain or something. So, there may be stuff like this where you have to figure out how am I going to avoid this, or if I have to put a cross-section there, maybe I need ineffective flow or something. So you just want to be aware of where you're putting your cross-sections and what that's telling HEC RAS. So once you've got your cross-sections in there, it's time to import them to HEC RAS. So, okay, so we'll go ahead and demo how to do that. I like to turn everything I don't need off. So here I've got the graphics for my top of bank and over bank that have been brought in as features, and I've got my cross sections. So that's all we'll need. Let me close some of these boxes so you can tell what I'm doing, so I can tell what I'm doing. So the first thing you want to do is see if you have your hydrology and hydraulics add-in installed. If you don't, you get to that through Tools, Application Add-ins. And if you scroll down through here, you should see hydrology and hydraulics. As you can see, I've already got it loaded, but you would just check that box and hit OK. So the tool we're going to use is under Evaluation, Hydrology and Hydraulics, Generate Water Surface Data. For our surface, you're going to want to select the drainage surface, and that has your top of bank and over bank features in it. It has your bridge removed, all your long triangles removed. It has your floodplain data. So everything that we've done is in that surface. Your alignment will be your stream center line, station downstream to upstream. And you want to create the section data, and the section format is HEC RAS. And maximum points, I think the maximum HEC RAS will use is 500, and so that's what I like to change that to. It's possible that you have more than 99 points in a cross-section, especially if you have LiDAR, floodplain data. Every time that this section crosses a triangle, it's going to drop a point and bring those into HEC RAS. So I don't want to lose any data, so I'll go ahead and bump that up to 500. Stream ID and reach ID will be imported into HEC RAS as the name of the stream. You can put something in there or not, whatever you want to do, and then units will be feet. So I like to use this little picker box here to select my left bank and my leftover bank and my right bank and my right over bank. And then our source is going to be a selection set, so we'll need to put all our cross sections into a selection set. And that's it. So 40 minutes to show you how to do that. That's pretty easy. Hit apply. It's going to ask you for a name. You can't really use HEC RAS and ProjectWise, so I always cancel. And I like to just put everything on my desktop and move it around later. So you could call it whatever you want. I'll call it import.go and hit save. So what that did is that pulled, every time these cross-section crossed the triangle, it gave a station along the cross-section and an elevation, and it put it into the format that HEC RAS uses. So now you'll have to jump over to HEC RAS and create a new project. And you probably title it the name of your stream or the name of your item number or something like that. And it's telling you that it's going to be set to US customary units. That's cool. That's what we want. Go to geometric data, file, import geometry data, GIS format. Navigate to your wherever you put it. Hit OK. So this is the import screen, US customary. If you hit next, it'll flip to the next tab. This is telling you that this is a new stream in Reach, and it's in replace mode. So if you were re-importing it, it would replace the old one with this. If you go to next here, it's showing you the station, all the stations where you've got cross sections that it's going to import. And it's telling you that these are all new. So one thing to note here is that you can do this, and then you can put a bunch of data into HEC RAS, and then you can change your cross sections and re-import it, and this will say exists instead of new, and you can tell it what of that data you want to bring in. So if you went into HEC RAS and adjusted your bank stations manually after you brought it in, you could turn that box off and it wouldn't import any of the bank stations. And I believe the way that would work is that it would save your old data. It would just re-import whatever you've got checked here. But I know that it will not remove your bridge if you've already put your bridge in and then you change your sections. If you replace that data, it will not affect the flow data that you've used in the bridge and stuff like that. So anyway, that's all you do. You hit finish to import data, and it looks remarkably like what we have here. So you can go back through and flip through your cross sections and see what they look like. I may or may not have something going on here that I want to look at on my DTM to see if that's indeed accurate. I can go through and move these bank stations out to there or something like that if I wanted to do that. But anyway, that's probably a topic for another day. You see I've got some problems here. My bank is not where it should be. But, you know, that's as easy as go in and type it in here and moving it. So you have to do a little bit of cleanup like that afterwards. But you've got the raw data in here to work with, and we can, I guess, talk about the other stuff at a future date. So the other data you're going to have to gather is going to be your bridge geometry, your flow data, N values, and you probably ought to be using horizontally varied N values. And then you'll have to get some ineffective flow data possibly, and if your road is acting as a levee or you've got some homes that are acting as obstructions or anything like that, you'll have to come up with, you're nowhere close to having your model completed, but you've at least got your raw ground data into HEC RAS. And this is just a public service announcement for the drainage section, but they're asking for a documentation narrative of why did you select your expansion contraction lengths, why did you pick your cross-section locations, why did you pick your N values, where did you get your flow rates. So instead of just getting a HEC RAS model and them having to try to decipher what you've done, if you could just include a short narrative of what you've done so that they can have an easier time of reviewing it, that would be helpful. Last couple things I want to mention. I'm not a GIS user. I'm kind of a GIS idiot. So I use MicroStation InRoads, and a lot of roadway designers do. So I'm more comfortable importing through that platform. But for GIS users, there's a program called HEC RAS, and it looks to actually have the capability of like importing your horizontally varied N values and your ineffective flow areas and all that stuff through GIS layers. So there's a link there if any of you are GIS users and want to take a look at that. It's an alternate way to bring that ground data in. Also, check out our developmental branches website. You get through highway design, and then on the right side, software and support. And we've got some more workflows in the queue that we're hoping to get up here soon, but one of them that's in the process is how to merge surfaces. And like I said, we'll be having that webinar in a couple of months. But there's our website, so there's our shameless plugs. And then I think on September the 3rd we're going to do, but my bridge doesn't look anything like the one in the example. And we've developed a little process of using InRoads and XML reports to get station elevation data off of a baseline that allows you to deskew a skewed bridge. And it might be a little more time involved than doing it by hand one time, but if you are in a situation where you're trying to make something work, and so you're anticipating taking you 4 or 5 iterations of HEC RAS models to try to right-size the bridge opening or something, it might be helpful for you. So that's what we've got coming up. That's all I've got for today. If there are any questions, I'll try to answer them. If they're more drainage related than technical related, then I'll probably pretend I didn't hear them and maybe ask the drainage section, and we'll send out an email. So that's all I've got now. If anybody has any questions.